All right, class, let's get started. All right, so a few announcements before we begin. I guess as expected, you should have all gotten another email from University Talk contact tracing. I don't know, I got 4 emails. I think I get extra ones as instructor, but I'm not sure how many exactly. I'm pretty sure we're still just up to 4 from last week. Per university guidance, so please mask through Monday of next week. It's really just about bringing that chain of transmission. I know you all spent a lot of time together. We don't want to have to keep doing this. And getting tested is free and easy. That's where I'm going after class to go do that. Today we have we're going to start by finishing off our discussion of momentum in the fluid. I guess we got a little bit held up discussing advection of momentum last time, so we're still going to finish up momentum today. We'll look at an example of how we can use what we've learned to measure the force required to turn a fluid stream. Then we're going to go into YouTube Friday. We're going to look at some videos, basically trying to use what we've learned about control volume momentum analysis to try to solve an interesting problem. Basically address whether or not a certain video is a hoax. Then we're going to start energy balance, and on Monday we're getting into Bernoulli equation. Homework 3 is out. Homework 1 and 2 solutions are available on Canvas. Homework 1 grades are available on Canvas. One note to you all, I just went through and did check to see who's using the Gradescope template or not. Seems like a few of you did not use it for homework 1. Please use the Gradescope template. It makes things a lot easier for the TAs to grade the homeworks. So please use that template that's provided. Okay. All right. Any questions before we get started? All right. Then we'll get moving. So the question that we're going to start today with is this example of a fluid jet competing on some kind of a deflector. And the question that we're going to address using the control volume analysis that we discussed on Wednesday is, what is the force required to hold this deflector in place? All right, so situations that we have something like I'm standing here with a garden hose or something, and the garden hose is being deflected by this fluid vein or this deflector. Okay? And that's going to require some force. Now, to get started, we're going to make a few assumptions here. So we're going to assume it's steady state. So we're going to assume that this deflector is stationary. It's just sitting there somewhere. It's not moving, and there's no acceleration. Right. So the rate of change of all our variables with respect to time is going to be 0. We're going to assume that the pressure everywhere is atmospheric pressure. We're going to ignore vane friction, vane weight, fluid weight. So the only thing that's happening here is that this fluid stream is changing direction. We're also assuming that the magnitude of the velocity is unchanged. Right? So we have the same magnitude of velocity coming in as it is coming out. And that's an important one, right? So what we're saying here is that so this fluid vein is not changing the magnitude of the velocity. But yet we're going to see that it still requires a force to hold it in place. Okay? That's going to be one of the key concepts that we're going to get out of this. So just by changing the direction of the fluid, we're going to require a force. So to get into this problem, we're going to start with mass conservation. In general, my advice for you, right, when you're starting a problem, you don't really know where to begin, start with mass conservation. Right? It generally will tell you something. It might not tell you much, but it will often tell you something that can get you started on a problem. Right? Remember, day 1 kind of defined fluid mechanics as application of mass, momentum, energy conservation to fluids. So far, we've discussed mass and momentum. But just because we're in the momentum section, don't forget about mass. Okay? So mass conservation tells us m.1 is equal to m.q is equal to m dot. If there's only one inlet and one outlet, all the mass flux in has to leave through that upper outlet. So m dot one is m dot two, and we're just going to call that m dot. It's not actually important for this problem, but what does this tell us about the area of the jet? So the velocity magnitude is the same at surface one as it is at surface two. You're going to tell me what happens to the area of the jet as it moves through the system. Yeah, it must be constant. Yeah, exactly. So why is it constant?
Because otherwise,
yeah, exactly. So otherwise, m dot would change. So m dot we can write as rho a times v. Density doesn't change, right? Let's say we assume this is an incompressible fluid. Velocity, magnitude, v doesn't change. That means the area stays the same. So the area in this system, the area here, is the same as the area there. So then we're going to do a one-dimensional or uniform momentum balance here, assuming that the velocity profile across this inlet and outlet are uniform, with velocity equal to v. And we get this right from Wednesday's class. So the sum of the forces is going to be the rate of change of momentum within the control volume plus the momentum that leaves minus the momentum that comes in. Right? What can we do? What kind of simplifications can we make to this equation based on our assumptions? Yeah. Yeah, so since it's steady, I'll repeat for everyone because the AC is blasting for some reason right now. So since it's steady, we're going to say this rate of change is zero, right? TTT is zero. Other things that we can do, like these sums here, are going to reduce. We can get rid of them as well, right? Because we only have one force being applied through that control surface at the bottom. There's only one outlet and one inlet. So we end up with this expression. The force is equal to m dot v2 minus m dot v1. Now note here, this is a vector equation, right? The force is a vector, velocity is a vector, v2 is a vector, and v1 is a vector. Okay, so we'll see that even though the magnitude of the velocity is not changing, this force is not zero. So the way your textbook describes this is graphically, and so I want to just go through the graphical explanation of this. So we could write the momentum in at control surface one as a vector, having magnitude m dot times velocity v oriented in this x direction. Right? Are you with me? And from that, we're going to subtract the momentum out at control surface two, which is also has the same magnitude, m dot times magnitude of v, but it's in a different direction, right? Because this vane has deflected the fluid upwards. And so what this expression tells us, this is a vector equation, right? And so it's telling us that the force required to hold this vane in place, the vector force required to hold this vane in place, is the subtraction of these two. Graphically, we can see this here. So this vector would be the force required to change that momentum. That makes sense? Right, so momentum is a vector. It has both magnitude and direction. So if we change either of those things, right, we require a force. In this case, we just changed the direction, not the magnitude, and that requires a force. Yeah, question.
Is it like normal to bend, something like that? Or that's a direct level?
Is it normal to the bend?
It's like the bend, the height or whatever.
Not quite. I don't believe it is. I do not believe it's normal to bend in that height. We can actually solve for exactly what direction it is in. Graphically from here, which is actually the next step in your textbook. That's a good question. I'm not sure. Okay, yeah. It is. I mean, as they've drawn it, it is oriented along, this structure. Right? You notice the angle of this is the same as this angle here. So we can use from this graphical explanation, we could use trigonometry to figure out the components fx and fy, and then solve for those components fx and fy. Again, remembering that this force is a vector quantity. Okay. So the key takeaway here is that the momentum balance equation is a vector equation. Okay. So the velocity, remember, is a vector, and the forces applied to our control volumes are vectors. Okay, so in this case, we had the magnitude unchanged, but the direction changed, and that requires a force. Okay, it's the main thing I want you to take away. So to actually get to this answer, I don't suggest you do this. So this kind of graphical solution is nice to explain the vector nature of all of this, but not the most direct way to solve this problem, I think. So I want to go through the way that I would solve this problem, the way that I suggest that you solve this problem on the next couple slides. But before we get there, any questions on this? Okay, and I said just some trig to get here, but we'll go through in more detail how I think you should probably address this kind of problem. So, so I think the easier way to address this problem is to start by considering the components x and y independent. Right, so we're going to do, remember we said that we can think of our vector equation for momentum balance as it's kind of one equation in terms of vectors, or we can think of it as hiding three equations, right? One for x, one for y, one for z. Why are we not talking about z? Why are we not talking about z today? Yeah, Michael.
Well, for one, it's easier to just deal with two versus.
It's easier to deal with two, okay, but when we use it in the example of the textbook, like why are we not dealing with z?
In this particular situation, we only have a chain and one, like it's y for y and x for okay.
Yeah, so in this case, there's no change in z, right? So our only change is the x and y, and so we're only dealing with the equation for the x and y. Or remember, in general, we live in a three-dimensional world, and so when we write a vector equation, we have three components, x, y, and z. The z component is hard to show on a 2D surface. It's another reason. We also can't bend the stream of liquid. There's no way for it to bend it.
Well, then you can just change your reference.
Yeah, he's saying you just change your reference point. Yeah, so if we had to bend, like come up and then over or something, we could change our reference point, right? And just change the way we draw the line. That's right. Yeah. Try to think it through. If anyone comes up with a counterexample, let me know. Okay, so I think the way that I suggest you do these problems is by considering each component independently, right? So we're going to solve for, in this case, x and y. We're going to do by using our force balance expressions that we derived on Wednesday. So again, we start out with, so we're assuming this is uniform inlet and outlets, meaning the velocity is constant across the inlet and the outlet. This is what we end up with, right? For force in x. Again, it's steady state. There's only one force, only one outlet, only one inlet. And so it simplifies to this. Our mass balance from the previous slide told us that m dot out is equal to m dot in is equal to m dot. That's actually going to pull out of here. So let's consider our control surfaces. So at control surface 1, which is our inlet, m dot 1, it's just m dot. Vx, right, the component of the velocity coming in at control surface 1 in the x direction is v, right, the magnitude of the velocity. Right? And then we do the same at control surface 2, which is our outlet. M dot 2 is m dot. And now the component of the velocity in the x direction is v cosine theta. And now we're going to plug this in to our expression, right? So fx m dot v cosine theta, that's out, minus m dot v. And if we put it all together, we get fx is m dot v cosine theta minus 1, the same thing we had from the trigonometry and the vector graphical representation on the previous slide. Okay. So this is the way you should probably do this. One thing I want to note here, just to call back to what we were talking about on Wednesday, hidden within this expression is the idea that y velocity can affect x momentum. Kind of glossed over it, but this is telling us that y velocity can affect x momentum. So you nodding your head. You know what?
Well, you're starting, like, yeah. Surface.
Yeah, so we have, I'm gonna expand upon what I think you're getting at there. So we have, right, in this case, we're just considering the x momentum, right? But if you notice here, this fluid that's leaving out of control surface 2 has some x momentum, but it's being carried out at least partially in the y direction. Okay. So at this surface here, we have some x momentum being affected by y velocity. And it's hidden inside of this term here. So let's look at that term. So we're saying that the momentum out in x is m dot v cosine theta. You can write m dot as rho av, right? So we can expand this out as rho av times the vx component, v cosine theta. Right, so again, this is the mass flux out times the x component of the velocity, right? But notice, this mass flux out has magnitude v, right? So this is not vx, this is not the x component of the velocity, this is the total velocity, including the y component. So this term here is hiding the fact that the x momentum is being affected by y velocity. That makes sense. Especially in light of what we discussed on Wednesday. So a common mistake that I'll see if you're starting with a form of this expression where you have like rho av times vx or something. A common mistake that I'll see this kind of problem would be getting the answer of rho av squared cosine squared theta, right? Because students will sometimes think, well, since I'm considering the x component, all of the velocities have to be just the x component of velocity, but that doesn't have to be the case, right? X momentum can be affected by y velocity. And I'd say when in doubt, just go back to the form of the expression that you're using, right? That's equivalent, that's appropriate for solving the problem, and plug in your variables. Don't skip a step. Okay. Question.
Is the v in the equation scalar or vector?
So v here is the magnitude of velocity, which is a scale. So that's correct. Yeah, so we've written this out now in terms of the scale. Good question. Any other questions? All right, so again, we're only considering the x component of the force momentum right now. All of the quantities here are scalars. Okay. So we can do the same thing in y. M dot Vy out minus M dot Vy in is going to be our force, the y component of our force. At control surface 1, Vy is 0. It doesn't matter that M dot is non-zero. Vy is 0, so there's no y momentum flux through that control surface 1. Control surface 2, we have Vy is V sine theta. And again, if we plug this in, we have Fy is M dot V sine theta. Again, the same answer that we got from doing the trigonometry and the graphical representation. Okay. So I just want to draw your attention to another example. I think I pointed this out in class some time ago as well. But on YouTube, I last year started uploading example videos where I go through these much more slowly by hand on an iPad while narrating what I'm doing and the assumptions and so on. And so I went through an example of basically the same problem, but on a cart that's moving. So problem 3.55 in your text. So I encourage you to take a look at this, especially if you're having some trouble with these momentum balances. Okay. Actually, as an aside, if there's any kinds of problems that you are having trouble with, definitely let me know. And as we get closer to the exam, I intend to record more and build up my library of these kinds of problem solving videos. definitely take suggestions. All right, any questions on this? You're gonna get some practice on your homework as well. Okay. Yeah, there we go. The energy in the room is definitely a little up. I know you're all waiting for YouTube Friday, but we're getting there. Okay. So just some tips on momentum before we discuss or watch a few videos illustrating some of these concepts and then get into energy balance. Momentum is a vector. Momentum equation is a vector equation. Almost like repeat after me. Momentum is a momentum equation is a vector equation. But don't forget that, okay? It looks like one equation, but it's really hiding three components, x, y, and z. Okay. Again, momentum in x can be carried by velocity in y, right? We saw that in this example. It can also be carried by velocity in z. Momentum in y can be carried by velocity in x, and so on, right? So, just because you're dealing with x momentum doesn't mean that every velocity in the equation goes to the x component of velocity. When we're talking about applied forces, they're acting on the control volume, so we can act anywhere on the control volume, especially on cut surfaces. So if we have a cut in the control volume through a solid material, as we did here, we kind of gloss over this, right? But if we have a cut in the control volume, if our control volume cuts through a solid surface, we need to include the forces applied at that surface in our force balance. Okay. So in this case, we cut our control volume cut through this this solid support. Therefore, we had to include the force on that solid support in our force balance. Yes.
Confirm the control volume of this equation, so it's the rectangle, so it's perpendicular.
Yes, the control, which is actually one of my next tips. So the control volume is this weird shape. Why is it in this weird shape again? Sorry. It's this weird shape so that it is perpendicular to the flow. Okay. Why do we make it perpendicular to the flow? There'd be math if it's not. That's a good example. So it would make it harder to keep track of. So remember in the full version of the momentum balance, we had a E dot N term that we evaluated at control surfaces. That E dot N is a lot easier to evaluate if your velocity is normal to the control surface. Okay, so otherwise there's math. Yeah. Okay. Yeah, otherwise there's math, and we can if we can avoid it, we might as well, right? There's gonna be enough other math that we have to deal with anyway. Okay. So another thing, and we kind of glossed over this as well, but another concept here is that the pressure at the exit of a subsonic fluid jet is the ambient pressure. So what does that mean? So if I have a like a garden hose and I'm spraying a stream of water, as long as I'm at subsonic speeds, right? I don't have some crazy garden hose. They'll go off. What we're saying is that the pressure within the fluid jet is the same as the ambient pressure. Okay. So when you're solving problems with these kinds of fluid jets and momentum balances, this is going to be a very useful assumption for you. We will look at exceptions to this, but so if you're dying to know what happens to get supersonic, but that'll be in chapter 9, so all the way at the end. And then the final note is choose control surface with normal to the flow. Okay, so just make your life a little bit easier and reduce the amount of math that you have to do. If you see if that helps. If you choose your control surfaces normal to the flow. Okay. All right. Any questions on this? Momentum balances, solving problems like this. Okay. So we're going to end show and go to our YouTube videos. So we're going to start with a video that I don't know, went viral sometime, in the mid-pandemic, sometime in 2020. So maybe you've seen it, but it's janitor turns head in Florida with a leaf blower powered vehicle. And the commentary was, is this a hoax, basically? because what we're going to see, well, let's just watch it, right? So is this a hoax? So he's sitting there. He has a leaf blower. Very happy with himself. I think life hack or something. And he's blowing directing the leaf blower against an umbrella, and it's pushing him forwards, right? Even though the leaf blower is pointing forwards as well. So what's going on here? So from a momentum perspective, can anyone offer a possible explanation for what's going on here? Well, why does it seem like it might be a hoax? Yeah, okay.
Well, it's like the air goes in front, like that has momentum of the leaf blower being this backwards.
Yeah, it seems like, so if you were to sit here without the umbrella, what would happen? You'd go backwards, right? Because you would have, you'd be pulling in air kind of from all sides through the leaf blower housing. And then directing a stream of high velocity with high momentum forwards, resulting in a force pushing you backwards, right? So that's what would happen if you get rid of this umbrella. But somehow with this umbrella, he's able to, or it looks like from the video, he's apparently able to direct himself in the opposite direction. Kind of like he's blowing his own sail, right? Which seems like it should be impossible. All right, so let's look at least one YouTuber's take on what's going on here. In this case, he's going to set up an experiment with this big flat sheet, so a big giant sail sitting in front of him, and a leaf blower, and he's sitting on a cart, and he's going to try to replicate what's going on, right? So is this a hoax?
And we're shooting up the leaf blower here. Let's see if it actually works. Okay. 3, 2, 1.
It's not working, right?
It's not going anywhere. To get this to work, take off the sail, turn the other direction, and
all right. So he used the big flat sail, and he was not able to get himself to move forward, right, by just blowing on the sail with the leaf blower. So case closed. Hoax? Yes or no? Who thinks yes? It's definitely a hoax. Just vote one way or the other. Who thinks no? It's not a hoax. Okay, I see more hands for no. Why? Okay, so why is it not a hoax?
Is it possible that he's shooting it to the head of the umbrella, so it curves around and then gets out the back?
It's possible that he's shooting it to the edge of the umbrella, so it curves around. Definitely possible. What I would say, what's different between the sail that he made and the umbrella?
Well, the umbrella curves in, which forces all the air to get front to backwards. With the flat sail, you can have it, you push up against it and it's spreading out the sides rather than backwards.
Exactly. So the umbrella is curved, right? So it's actually able to redirect the air backwards. So the same YouTuber came back with another video and another contraption trying to explain what's going outside. Yeah, and the sail went to the side because it wasn't catching all the air. And meaning it was going to be redirecting the air to the side as well, which could result in a force. Yeah, so the same YouTuber comes back.
doesn't work. So it's not going anywhere. So the problem with the setup that I showed before is that it's using a flat sail. So what happens if you use more traditional sail that's curved? Now let's see what happens when I use a sail that directs a lot of the air backwards. So I just put a box on here. I'm going to turn on the fan and see if it can actually blow itself forward. So let's see what happens when I turn it on. 3, 2, 1. There it goes.
So yes, similar contraction. So now he's built a contraption with not just a flat sail, but with something to redirect the air backwards. And now, as expected, it actually doesn't float, right? So potentially not a hoax. Mythbusters has their own take on it, which is just like entertaining to watch.
Funny part of the whole experience, when you first turned on that fan, and the boat just started to spin and did down in one direction. Where it's not boat would be still over.
Why are they spinning around? For momentum. Why are they spinning around? Because it's angled. What do you mean? Why would that cause them to spin? Yeah, so if we're have the air coming off the sail at an angle, then we're changing the momentum of that airstream. The result is an applied force on the weird kind of boat contraption. In this case, that force is not going to be directing them forward, but it's going to be spinning them around instead, right? So again, we understand that the same way from a momentum balance explanation. And they go on, they actually make this work. It requires some very careful control in order to make it happen. But again, we can understand this just using what we've learned right in class just the past 2 days. Is there a question? Okay. And now I promised video, I promised that we would look at a video of snapping shrimp. And so we have one of those. But this will actually lead us into one of our next topics, sort of explaining one of the things that happens here. But let's watch. I just want to stop for a second there. So we talked about this as an example where the pressures inside are so extreme that if you really want to analyze what's happening inside this claw, we'd be violating heat compressibility of water, right? But there's something else happening. That high pressure is creating a fluid jet. And he just said that the fluid jet is so fast that it vaporizes the water. How does that work? We don't know yet, right? So we're going to explain that with Bernoulli equation, or with the Bernoulli principle, which we're going to get into soon. Okay. So but what we're going to learn is that we're going to treat the Bernoulli equation as a form of energy balance. So we're going to look at a form of the energy balance, which is going to discuss trade-offs between the pressure within a fluid and the velocity of the fluid. And so it'll show us that as the velocity increases, the pressure decreases. And in this case, what that will tell us is that if we increase the velocity enough, right, like in one of these pistol shrimp claws as it's snapping, then the pressure can get so low that we go below the vapor pressure of water and actually cause a cavitation bubble. Okay, but that's where we're headed next. So we're going to go back into our discussion of balance equations, and now get into energy balances, right, as our next discussion. Okay. Any questions before we move on to energy? Really sorry about this. I'll try to have this fixed. Talk to the HVAC people and they'll fix the runaway HVAC, which makes it very hard to hear what's going on within the room. All right. So just as a reminder of where we are. So a few classes ago, we developed the Reynolds transport equation shown there in the upper right, which tells us about it's basically an equation for balance of stuff within the system. We said P was some quantity we want to track through some control volume, and that Reynolds transport equation, in a general way, tells us about the creation or construction or conservation of stuff. Right? We looked at it as that stuff being smoke in a video example we discussed. Then we said that we let B is equal to M, or mass, if beta was just 1, and we derived an expression for conservation of mass. Right, so we're through there. Then we did momentum, right? We said that B now was going to be a vector quantity equal to the momentum m times v. So beta was just the velocity. And we saw that the sources and sinks of momentum, we said sources and sinks are momentum by Newton's second law, Fx equal to ma. And then we developed an expression for momentum balance in a fluid, right? And then now again, remember I said in this class, we're going to do mass, momentum, energy balance. So the next thing to do is to say that B is E, or energy, total energy in the system, and the control volume. Now beta is going to be little e, where little e is the energy per unit mass. And now our sources and sinks of energy are going to be work or heat, work done in or on the CV, or heat added to the CV, or taken out of the CV. Okay. And now when we look at this little e energy, we're going to say that this energy is going to be equal to the internal energy of the fluid. So this little e is energy per unit mass. It's going to be the internal energy of the fluid plus the kinetic energy of the fluid plus the potential energy of the fluid plus other things. Where other could be chemical or nuclear reactions, electrostatic interactions, or other things. We're mostly going to be ignoring those, right? Those are for other classes. So we're going to look at internal energy, kinetic energy, and potential energy within a fluid. And now this balance equation will let us track how those things change through control volumes. So ignoring those other terms, we can rewrite this little e, the energy of the fluid per unit mass, as the internal energy of the fluid. We're going to write that as U hat in this class, plus 1/2 b squared. That's the kinetic energy of the fluid per unit mass, right? 1/2 mv squared. If we had a baseball traveling across the room, we say that the kinetic energy of the baseball is 1/2 mv squared, right? Where m is the mass of the baseball and v is the velocity which it's moving. So the energy per mass would be 1/2 v squared. Same thing for a fluid, right? And similarly, our gravitational potential energy per unit mass is gc, right? Total energy would be mgc, but per mass we just get g. So now we can track. We're going to track those three terms. So internal energy per unit mass, kinetic energy per unit mass, and gravitational potential energy per unit mass. And then when we put this in, then we're going to be putting this into our Reynolds transport theorem. And to put this expression where I can substitute out for little e those three terms, right? So it's telling us the total change in energy within the fluid per unit time is the change within the fluid contained within my control volume plus the stuff that moves in and out over my control surface. Right? Here I'm using the form where I have lumped my inlets and outlets all into one term, which I can do because it's v dot n. Right? Remember, n is my outward facing unit normal. So by writing it out this way, it's v dot n. I'm going to automatically account for my inlets, my inflows and outflows in this expression. And then simplification, right? The same simplifications that we're going to make the same kind of simplification that we made in mass and momentum, but now just for our energy balance. So since we've done this twice, we'll go a little bit faster for some of this, and then we'll slow down on some examples and defining what these terms are, which are different. But if my inlets and outlets are 1D or uniform, then I'm going to end up with dEdt is the rate of change within the control volume of my energy, plus the energy flux out minus the energy flux in. Okay. With me so far. Okay. All right. So back to this example. So we looked at this example when we discussed the mass balance equation for one-dimensional inlets and outlets, right? And we saw that in this system, mass was conserved, right? We said that in this class, mass is not going to be created or destroyed, and in this system, in fact, mass balance was achieved. Now we want to ask what happens to energy within this system. right? So what is the net change of energy within this system? How should I get started? What should I do to get started on this problem? I need a hand raise. Yeah, okay.
Use a mass flow rate in every stream.
So we need a mass flow rate in every stream. How can we find the mass flow rate from what's given in every stream?
Density times velocity times area.
Density times velocity times area, right? So rho times A times T is going to be giving the mass flow rate. I have the energy of every stream, right? And so I'm going to be able to find the total dE dt, the total change of energy within this system by using the expression that was on the previous slide, right? So we'll start with our assumptions. We're going to assume steady, fixed control volume is not moving, uniform inlet and exit flows. So we have the EDT is the rate of change within the fluid within the control volume, minus the inflows plus the outflows. And since we're steady state, this term drops out. Here we've expanded out our inlets and outlets. And we have all of these terms, right? We have E, we know M dot is rho AV. And we have that for all inlets and outlets. So in this case, we can just plug this into our expression, right? So we start with this simplified form of the expression. We can expand it out. M dot is rho AV. In this case, all the M dots are not equal, right? Because we have 2 inlets and 1 outlet. So we don't just have M dot 1 equal to M dot 2 is equal to M dot. We have a few to keep track of. And we can plug it all in, right? So we plug in all those numbers. We get negative 240,000 joules per second. So what's going on here? Yeah, Francisco. So remember, these are the Reynolds transport equation. We have a balance equation, right? So we're saying that, so in this case, the balance equation implies that our inflows are greater than outflows. So we have to be pulling energy out of the system somehow. Okay. So dE dt, we're pulling energy out of the system somehow at a rate of minus 240,000 joules per second. Okay. That's what this is telling us. Yep.
So in real life, that we determine stream points who are like bumping each other in the direction, and that way they can move energy. What would cause it?
Yeah, so what would cause a change in energy is actually going to be my next question for everyone. which is a great segue. So I'm not going to answer you just yet, but you will get your answer in just a second. I saw another question though. Okay. What do you have? Heat would definitely be one reason. We could be turning a turbine or something else. Yep, that was actually my class exercise that was about to come up. So to balance out the energy, so maybe we'll skip through it then. So to balance out the energy change, there must be some net energy that's lost from the system, right? It could be heat, it could be work that we're pulling out of the system, it could be something like that. So my exact next question, which now is an answer for all of us, is how can the energy of the fluid change? What makes up the E to T? And since we have our answer already, I think we're going to skip ahead to what happens. Does everyone, can anyone else give me the answer? I guess it's noisy in here. So how can the energy of the fluid change? Yeah. Heat work. Heat work. What are the ways that I can do work on a fluid? Or get work out of the fluid? I can make it spin something. Yeah, yell louder because of this thing. What are the other ways that I can have that I can take work out of a fluid? At the boundary, I heard at the boundary. What do you mean at the boundary? What can happen at the boundary? Oh, a moving boundary, right? So a moving boundary, we'd probably lump that into like some kind of turbine or that kind of thing. What else can happen? What are the other ways at a boundary of a fluid I can take work out of it? Yeah. Expansion contraction work, and that would be exerted through what kind of force on the fluid would be expansion? Pressure, right? So pressure in a fluid can be used to do work. All right, there's one more, and then we've actually gone through the material on the next 2 slides. So one more way that I can get work out of a fluid. Yeah. Shaft work is going to be when we say a turbine, we mean a shaft, right? Because typically we have some kind of shaft that we're turning with the turbine. So we're going to call that shaft work. There's one more term. Heat exchanger. So heat exchanger, we're talking about heat, right? So we talked about pressure, yeah. Viscous, yeah. So I think you said viscous. I can't actually tell. Yeah, what did you say? Oh, a piston. Yeah, yeah. So that would be something we'd probably include that in our pressure that we're gonna take out of it. So I said the answer, viscous work, right? So we can have we can pull energy out of a fluid by viscous drag. So we're gonna say energy can change because of heat and work in general. So this dEdt, right, that negative quantity that we got in our energy balance can be explained by heat, right, by pulling heat out of the system, or by using the system to do some work, right? We didn't show a turbine shaft in there, but if they're having a turbine shaft, that could account for the negative dEdt, right? This is an image from Van Dyke showing kind of both. So this is the convection cells in a rotating annular space heated at the rim. So we have the inside spinning relative to the outside, and the outside is heat, right? So we're adding heat, and actually in this case, putting work into the system. It's a complex flow. But something to note here is another sign convention, right? So remember, we've had a few of these come up, and they can lead to confusion. So this is something to pay attention to. dEdt, we're going to split it into two terms: heat added to the system and work. And by convention, we'll define positive Q as heat added to the system. All right, so positive Q is we're putting heat in, and positive W is work done by the system. Right? So in our example before, we had dEdt negative 240,000 joules per second, right? So that could either mean that my Q was negative 240,000 joules per second, right? My dQdt was negative 240,000 joules per second, or my dWdt was positive, right? Either of those would explain my negative 240,000 joules per second energy loss of the system. Yeah.
And energy loss of sound, like if you are sonic.
Energy be lost to sound, definitely. I mean, energy can definitely be lost to sound. We don't have a term where we're going to be considering that. I mean, in some sense, I guess it all depends on the frequency. But yeah, we don't have a specific sound energy term. Definitely energy.
Are there instances where that could be like important, or is it all?
The question is, are there instances where it would always be important or always negligible? It could definitely be important. If you have something like a race car and something's flapping around, making a lot of noise, that's energy that's going somewhere that you don't want to go somewhere. Another case where it's important, also aerodynamics, is aircraft, right? The energy lost through sound is important from both an efficiency standpoint and also just from like a disruption of neighborhood standpoint. So actually, like aeroacoustics is a big field of research, right? So how we deal with how fluids transfer energy into sound is actually a big active field of research. Boeing cares a huge amount about how much noise they're generating, because that determines where they can fly, right? Like whether they can fly over the Salt Lake Valley, and how low and everything is determined by how much noise. All right, yeah, Simon. Yeah, so the difference between work due to viscosity and work due to pressure. We're actually just about to talk. The next couple of slides we're actually going to have to get to on Monday, unfortunately. We're gonna split this dWdt into three terms. The shaft work, which is like turbines, pressure work, which is by pressure forces, and then viscous work as well. And we will discuss that on Monday. Okay. All right. Any other questions before we break for the weekend? All right. Thank you all. Yeah, remember to vote in the SAC election.